time consuming. Every single possible combination, and it's like, oh, that's stupid. It's important, I guess.
Yeah, I'll tell you why I agree. It is stupid, but I'm going to tell you the alternative is more stupid.
Well, I know it's important, but it's annoying.
Yeah, I agree. Alright, so. Oh boy. Titus. Which one is the good one? He went crazy on my board yesterday, so I'm pretty sure all these markers are no longer good. I'm guessing I'll have to get another one. I swear I gotta go for more markers than anybody in this whole school. Okay. So sometimes there's more than one valid Lewis structure. Point in case. Wow. I'm pretty sure that camera can't see that.
It's an N in the middle with three single bonds, two single bonds for oxygen and a double bond of oxygen. The oxygen
Alright.
the octet rule. There is a
Thank you for the commentary, Rylan. It's putting Grant to sleep. It's like Morgan Freeman, a documentary.
I wish.
Okay, so as you guys are already aware, there are some guys that have a structure where you have to make a decision as to, okay, since I have the same element surrounding my central atom, where do I put the double bond?
Anywhere.
Because theoretically, we could put that double bond in any one of those three locations and it would still be stable, correct? Okay? Now, there really are two types of bonds here. There's a shorter, more stable, strong double bond, and there is a longer, less stable, weaker single bond. So what I'm trying to point out here is this bond and this bond aren't the same. Right? They're not the same lengths, and they're not the same energy required to break them. We agreed on that when we talked about bond energies and bond lengths a couple days ago, correct? We looked at the book and the table, and it said a carbon single bond is different than a carbon-carbon double bond, and different than a carbon-carbon triple bond. They had different energies, right? Okay? Some were more stable than the others. Okay, the triple bond was the most stable, the double bond was the second most stable, and your single bond was your least stable. Okay, and how did that relate to bond length? Does long length mean stable, or does short length mean stable? Shorter length means stable. Okay, shorter length means it's held tighter, it's much stronger. Okay, and it means low energy. Okay, so we look at this and we say, okay, we got a double bond here and two single bonds. Here's the problem. Okay, here's the problem with this. Is that when we look at the experimental data or the experimental results of this particular molecule, what we find is the bond energy and the bond length of these three bonds here are exactly the same. Identical bond lengths, identical bond energies.
You don't know which one is double.
Wow. In reality, the assumptions that we make is that none of this is correct.
They're all kind of double bonds.
There are no double bonds and there are no single bonds in this guy.
They're strong.
It's a hybrid of all of them. Okay, now, this is a man-made theory. Okay, but the experiments show that that there's only one type of bond here. Okay, it's only one type of bond, same bond length, same bond energy, and that bond length and bond energy is somewhere in between a single and a double bond. It's not a single, it's not a double bond, it's somewhere in between, and all three of those bonds are identical. Interesting. Okay, so are any of these structures, if I were to show resonance, if you guys remember what resonance is, if I were to show resonance, which I know it's tedious, yeah. It's not difficult more than it is annoying. Why? Alright, where did I put it? Okay. Okay? Which one of these is correct?
None of them are at all.
None of them are correct.
And all three of them are.
Okay? So really what it is here is we have to make an assumption. The correct, really Lewis structure of this, it's neither of them. Okay? It really exists as a hybrid of all three, or what the book would say, a superposition of all three, which means they all overlap, and it's somewhere in between. Right? If I overlapped all of these, it'd be somewhere in between. So if I overlapped all of them, I'd have a double and 2 single opportunities. So what that means is 4 total bonds, 2 from the double and 2 from the single, 3 times. So really, the bond length and bond energy is a 1.33 bond length and bond energy. What that simply means is that all 3 of these bonds are a hybrid in between a double and a single. And that hybrid is approximately 1 1/3 longer than a single bond. Sorry.
Stronger.
Short. Yeah, stronger than a single bond, I should say that. So then it would be shorter, yes. Does that make sense? Okay, so what they're saying is this, and this, they're not a single, they're not a double, they're a hybrid of all 3. So instead of saying 1 double and 2 single, it's 3 1.33 bonds.
So they're all equal.
Weird. And that has to go into the idea that when things bond, they form completely new hybrid orbitals. The old orbitals that they originally had are no longer existent. I know, it's deep stuff. Now remember, these are man-made models to try to explain what experiments show us. So is this actually the correct thing?
We don't know.
We don't know. But if we change the model to this, it at least agrees with the experimental data. Now, is our explanation of it correct? We have no idea, but it, at least in theory, makes sense. Okay? So it's really not any of these. It's a hybrid of the 3. Okay? And in this case, it would be a 1.33 bond. So what I want you guys to do, if they do ask you for resonance, I do want you to show this, because here's what the alternative is we have to have a completely new way of doing Lewis structures, where you pull out a ruler, and you have to measure. There's no such thing as a single, double, or triple bond anymore, and there's just a bond length and bond energy, and you have to measure out, okay, a single bond is 1 centimeter long, a double bond is 0.5 centimeters long, a triple bond is, 0.25 centimeters long, and when you have a 1.33 bond, it's this long, 0.76 centimeters long. You see what I'm saying? How the alternative is to actually get a ruler out and have no more single, double, and triple bonds, instead having your hybrid bonds where you actually have to pull a ruler and measure them. Does that make sense? So, yes, I know this is tedious, but the alternative is quite more tedious. Quite a bit more tedious. Quite more tedious. Okay? So, here's what I want you guys to do. I think there is another one that you can show resonance for. This one? You guys have this in your notes? Is that correct? Can you guys see this red marker okay?
Yeah. He is erasing the red marker off.
Okay, Riley. We gotta get to formal charge here, so I want you to quickly go through this. And then I'm really hoping you can tell me what the hybrid bonds are gonna be like if you compare them to a single or a double bond.
that's 0.76.
What's that?
Yeah, because 1 divided by 4 over 3 is 0.75.
Nice.
It's 1 times 3/4. Yes,
It's just a guesstimate.
you guesstimated really good. Good job.
But you guys can understand why it would be tedious to have to, like, since there is no more single, double, or triple bonds, they're just as bond length and bond energy, how being able to describe a single bond length, a double bond length, and a triple bond length would be very difficult. Not to mention that not all single bonds are the same length, right? A carbon-hydrogen single bond is not going to be the same length as a carbon-carbon single bond. This is a tough one? No? What?
When it's described, I mean draw the structure.
Yeah, show the resonance.
Okay, then I think there only be one. No.
Yeah.
It's 1 double bond, 1 single bond.
Yeah. It's a double bond and a single bond. I need to show you?
Because nitrogen has three spots available.
So I got an oxygen here. Oxygen here. Okay, let's just form a single and a single. Now remember, nitrogen cannot disobey the octet rule. It's in group 2. It doesn't have any D sublevels. So because it can't disobey the octet rule, what's going to end up happening is it's going to form a double bond with one of them, and then your excess electron is going to go to the other oxygen. What you have is this, and then your resonance would just be showing the other structure. Okay, so who can tell me what these bonds are? Because technically, is this a single and is this a double?
No.
No, it's not. Okay, so how do they relate then? What are they actually if we were to experimentally?
1.5 bond
Yeah,
strength.
they would be a 1.5 bond strength, because if I were to overlap them, we would have, it's either a single or a double. So you have 3 bond chances in 2 locations, 1.5. Now, what we would say is both of these bonds are equivalent bonds of 1.5 length and strength.
How would
Make
that
sense?
change if there are different types of atoms bonded to the same center one?
If they're different types of atoms, you wouldn't have to worry about where the double bonds go. It'd be pretty obvious.
Well,
Usually.
what if carbon was in?
I mean, the only thing I could say is if this was like a sulfur, but I don't know if that's going to happen.
Okay.
Yeah, not that I'm aware of.
Okay.
Okay. Questions?
If it was, would double bond always go with more electronegative one? I mean, theoretically, or at least maybe.
Probably, because it's going to be held tighter, so it would be a shorter bond length. Again, that's all speculation. I've never come across any of that.
Okay.
Okay, so let's figure out exactly how to determine what type of Lewis structure, whether, especially when we start getting the guys that have the ability to disobey the octet, how are we going to determine which structure it will form? And that has to do with formal charge. Okay, so what formal charge is the difference between the number of valence electrons the lone atom or the atom that wasn't bonded had, and the number of valence electrons assigned to the molecule, atom in the molecule. So you're probably wondering, how do I know how much electrons are assigned to a particular atom when it bonds? Well, there's a specific equation that we're going to use that will help us with this. Okay, you can imagine what the electrons are on the free atom would be, right? So if I'm talking about oxygen, how many valence electrons does the free atom of oxygen have? 6. Okay, so that's pretty straightforward. But let's figure out how we do this. Ooh. Shoot! I think I was supposed to print off a sheet. Do you have?
No.
You don't have anything?
No.
This will take forever. We're in chapter 8.
Yep. 8, 12.
What in the world? I don't have a copy of it, or an electronic copy of this?
Probably did, 'cause I took less box too. That's cheese.
Darn it.
The scores.
They're in?
Yeah.
What'd you get?
I'm not looking yet.
Man, now I'm scared.
Yeah, I know.
For ACT?
Yeah.
They're in way faster than the SAT.
You
Oh,
take
is it
the SAT?
SAT?
No, the PSAT, sorry.
Oh.
The ACT scores are in way
gosh.
faster than the PSAT.
I don't know, I would like wait till I get
already got
home
it
first.
27.
How's mine not even good? I'm really fun.
If I did worse.
27 was not that bad.
Yeah, no, that's what I'm saying. Like,
Wow, okay.
this time I don't really care. I just did it.
Emily, is this your first time taking ACT?
No, it's my third.
What'd you get the first time?
Well, the last time I think it was 26.
That's pretty good.
I think I did a lot better on the reading this
I'm
time.
not thinking about your math.
You know what?
though. I think I'm bombs in math.
Okay, I don't know why I don't just put it in the notes. It seems really.
Did you click the middle one? It's the last one.
B scores.
They got their
It was like
ACT
a week
results.
ago.
Who did it? How'd it go?
I didn't look at it.
B scores.
What day is it?
Excited to look.
Oh,
Sure, you go.
Yes, we're gonna talk.
Oh.
Oh, thanks, Cameron.
Did you good?
Doesn't look good.
You haven't looked yet, or?
No.
Why would you,
Alright, well, I don't know.
Cindy,
They are what they are. So
Yeah.
just know that I got a 27 the first time, so this one's not as good.
It isn't as good?
It might not be, I don't know. We'll see.
Why you don't think it was as good?
Dang it. 26, what's my deal?
Still not bad.
Was it the same? Did you take the same test?
Oh, I got a 10 on the right.
I don't know what.
You took the
That's
right-
it.
I have 12. That's like.
Wait, there's a writing portion on the ACT?
You can
Yeah.
take
It's
it.
optional. Why would
You look.
Why did you take it?
I don't know, my parents made
Okay, does that make it harder?
Did it tell you what you got in each?
Well, the test took it with the writing, she got lower too, so it might speak as the writing.
it. I got higher on the writing
Oh, you took writing both times?
though. Yeah.
I didn't take the writing thing.
Yeah, it's
I didn't feel like I could write enough and writing quickly.
Alright, well, we got formal charge reading to do. But I do want to, I do want to see. I do want to know what you got.
See.
Yeah?
I got 28.
Yeah! What'd you get before?
26.
Nice! 2 points higher. What made the difference? Did it say?
Oh, I got lower in reading. I got, oh my gosh! I got a 24 in English last time.
Uh-huh.
I got a 32.
What's that?
I don't know. I'm gonna look at
That
something.
probably means science went down.
Science was a 23 last time. I got a 25.
Nice. How did you only go up 2 points if you had an 8-point increase in reading?
Because my reading.
Your what went down?
Reading.
I heard English went up reading.
But my math.
Nice! Mr. Darrell is teaching you some stuff, I guess.
I guess so.
Okay.
Yeah.
Let's do it.
Sure. That's it.
So, I gave you, there's a lot on there,
Yeah.
okay? But some things that we need to know. In order to determine your formal charge, we must know 2 things. Number 1, the number of valence electrons on a free neutral atom. Okay, so we need to know how many electrons are on the free atom. We need to know how many electrons belong to the atom when it's in a molecule form. Okay, so then you have an equation here, formal charge. Did you study for the English portion?
No. Actually, I watched some videos. Here we're on.
Yeah. I'm pretty sure I got it. Just take it.
That's what I
Oh,
wanted,
okay.
like, I get 30, I'm like, I know, I'm like.
I'm gonna read it.
I'll go with you.
Yeah. Well, I did pretty well in math and science.
Okay, well, I just want you guys all to know you did way better than I did.
I guess I don't know how to respond to that.
Well, I didn't take any yet, so.
did way better than Kramer.
I'm pretty sure you will.
We're the only ones that have to
That's okay. I mean, it's stressful, but it's not horrible. Like, it's bad, but it's not bad. It's not pleasant to take, but it's not as bad as some of the.
Okay, so here's how we figure this out. Okay, to identify the formal charge on each atom, we have to know the number of electrons on the free atom, and then the number of electrons that is assigned to the atom in the molecule. Okay, well, we've identified how to figure out the free atom's electrons. We have not identified how to identify how many electrons are assigned. So if we keep looking here, it says to determine formal charge, we need to know a couple things as far as how do we assign them. The first, it says lone pairs belong entirely to the atom in question. Okay, so if I'm doing something like this, all right, this is a molecule. This is how this would bond. Okay, so it would have these two lone pairs are entirely belong to the oxygen. Okay? Then it says shared electrons are divided equally between the two shared atoms. Okay? So what you would have here, number of valence electrons of the free atom would be 4 minus the number of valence electrons assigned to the atom in the molecule. Okay, so how do we figure out how it's assigned? It says valence electrons assigned there. Everyone see it?
We have lone pairs.
Okay, it's lone pairs plus half the shared electrons.
So half of them.
It would be this. It would be the equal amount of bonds because each of these
Oh.
bonds represents 2. Okay, so there would be 2, 4. Half of that would be 2. That's it.
Yeah.
4 minus 2. That's not. Yeah. No, this is not right. 6 would be free electrons minus 4 plus 2. Your formal charge on oxygen is 0. Everyone see what I just did there? Okay, this would be how many oxygen had before it bonded. It was 6, right? This is the number of valence electrons. This is the number of lone pair electrons plus the number of assigned electrons, or the number of bonded electrons, half of them. Okay, following? Yeah? Okay, let's do one a little more difficult. Instead of pulling up, well, yeah, let's pull it up.
So if it doesn't equal 0, you did it wrong.
Yeah. I'll show you.
They
This will
want-
make more sense when we do a problem.
They want as close to 0 as possible.
Yeah, they want to be as close to 0. Oh wait, I don't even have a problem up here. This is cheap.
Or is it negative?
What is the problem that I have here?
You don't.
Do I have anything?
No.
Alright, so let's do SO4 2 minus. Did I give you a space at least?
Yeah.
Okay? So there's a variety of ways to show this guy. Let's start with the first one. Form single bonds. Now I could take these 2 electrons on sulfur and move them to the oxygens, yeah? One here, one here. And then my 2 negative charge could go here and there. This is one possibility of the Lewis structure. Well, here's another possibility. So eyes up here for this guy. How I did this one is I took that other electron and formed a double bond, and then the 2 excess electrons went on these 2 guys. That makes sense? How those are different? The question is which one is the correct way? And the answer is the one that has the least formal charge. Okay, so we need to figure out the formal charges on each of these guys. Okay, first thing we need to figure out is the valence electron assigned. Let's start with sulfur. Valence electrons assigned to sulfur. If we look at this guy, do I have any lone pairs?
No.
No. Okay, so our valence electrons assigned, if we look at our little sheet here, where is my sheet? I don't have it anymore. Where did I do it? Oh, there it is. Okay? If you look at how you assign your valence electrons, this is the number of lone pair electrons plus half of the shared electrons. Okay? Well, how many lone pair electrons do we have? Plus half of how many shared electrons are there? 8. So sulfur has 4 assigned electrons to it. Okay? Let's figure out how many valence electrons are assigned to oxygen. Okay, since all of these oxygens are identical, this will be nice and easy. I've got 6 because they have the 3 lone pairs, plus 1/2 of 2, right? So 7. Alright, great. Now, let's figure out the formal charge of each of these guys. Okay? And formal charge is going to be the number of valence electrons on the free atom. So what would sulfur's free atom number be? 6. 6 valence electrons to begin with. Yeah? So it'd be 6 minus the number of assigned ones. How many were assigned? 4. What's the formal charge here? 2. Plus 2.
Where'd you get the 6 from?
Sulfur has 6 valence electrons if it were alone, a free atom. That's what this one says. Number of valence electrons on a free atom. That's saying how many valence electrons did it have before it even bonded. Does that make sense? Okay? The 4 is what the assigned electrons were. So it's free atom electrons minus assigned electrons when it bonds.
So you can do the formal charge of O or N.
Yeah, well, you can do oxygen first and then sulfur, but they're separate. Does that make sense? Okay? Now, let's find the formal charge of your oxygen. Okay, how many of electrons does it have in its free atom? 6, it's oxygen, right? Minus the assigned. Formal charge is? So all the oxygens have a -1 formal charge. Now look at this. Your formal charges should add up to give you your overall charge. Do they? Okay. Let's do this one. Let's see which one's the best one. Questions? Anybody? Okay. Sulfur, oxygen. Okay, don't leave. Okay, let's start with a sign. How do we find a sign? Sulfur.
0 minus 1.
Okay, so it'd be 0 lone pairs plus half of 12. What, 2, 4, 6, 8, 10, 12? 1/2 of 12 is 6. Okay, now I've got 2 different oxygens. Don't we already know the assigned for this?
Yep.
What is it? Okay, and then the other oxygen is going to be this one, which is going to be 4 plus 1/2 of 4. 1/4 of 4. 1/2 of 4 should be 6. Okay? So let's find the formal charge of the other. This is the formal charge of this one. So we know that's -1 and that's -1, correct? We know that from what we did over there. Make sense? So I'm just trying to not rewrite it. Okay? Then we've got an assigned of 6 here. So let's figure out the formal charge of the second oxygen type. Free atoms would be 6. Minus 6 is So these guys do not have any formal charge. Okay? So the same thing for sulfur. How many would be on free sulfur? Minus the sign. There's no formal charge on that. Does it still add up to give you your overall charge? Which one is the correct Lewis structure?
Both -2, so I'm not sure.
Which one has the least amount of formal charge? The one on the right. This only has 2 guys that have a formal charge. Here, all of the guys have a formal charge. This would be the correct Lewis structure to write. Okay? So, on a test, when you're doing Lewis structures with octet exceptions, you need to figure out which is the correct way to write it based on formal charge.
So it doesn't necessarily always just obey the octet rule.
No.
So,
You're saying if it can obey the octet rule, well,
Obey the octet.
yeah, notice how this obeys the octet rule, but it isn't the correct Lewis structure. Yep. Okay, and that's really where it's a step beyond what we talked about in regular chemistry.